for still staying, I guess, for this last talk of this particular session. So today I will be talking about the peer-to-peer overlay of blockchain systems, and in particular the XRP ledger, and what kind of things we can say about its resilience to adversarial attacks. And towards the end, I will also try to give some ideas on perhaps improving the resilience. Let's look at some motivation here. So we know that most blockchain systems run on a peer-to-peer overlay. There is no decentralized server. The communication, let's say, particularly about the blocks, have to go through the links of this peer-to-peer overlay. What this means is that the resilience and overall security of the blockchain system will also depend directly on this peer-to-peer overlays topology and its robustness properties, again, with respect to adversarial attacks. I'll talk about our attack model, but it will be quite simple. Let's say, an adversary removes a bunch of nodes, maybe using something like a denial of service attack. Let's look at our data set. So we have used this particular paper that already collected the XRP's overlay network from January to May 2022. The two things I like you to keep in mind about this network topology are the number of nodes is around 1,000, let's say 950. The average degree is about 16, and when I propose maybe some ideas about making this network more robust, maybe that 16 number can come into mind, because I will propose a additional construction to the peer-to-peer overlay that will add only 4 edges per node on average. The other things that could be of interest in this maybe table is the average shortest path length is about 2.3, which means that every pair of nodes on average needs 2.3 hops to connect with each other, and the diameter is basically the largest distance among pairs of nodes in this network. So let's look at the resiliency analysis and what we exactly are looking at, or what do we mean by the resilience of this topology. So again, this is maybe looking at from a more network science perspective without going into too many practical aspects of how an adversary could attack a system like this. But essentially, we assume an adversary is capable of choosing a subset of nodes and removing them from the system. And what we are interested in is what happens to the rest of the network. And one typical topology metric is basically this, what we can call as S of P. If I am removing P fraction of the nodes, S of P is basically the fraction of nodes that still remain in the connected giant core of this network. So what we are typically interested in is going to be like a plot like this. I mean, this is just an example. It is not from the XRP. And one thing you can realize is that if the adversary kills P fraction of the nodes, best case scenario, the remaining 1 minus P fraction is still connected. So the best fully connected topology would give you a picture like linear decay from basically with a slope of 1 minus P. And other things you can look at, maybe once you get a plot like this, could be what is the critical attack size. You can call this the moment the entire network collapses. Essentially, there is no really substantial connected component in the network. And sometimes we are also interested in the area under this curve when we evaluate the robustness of a topology. Let's look at some results from the XRP's peer-to-peer overlay. And as I mentioned before, the best scenario you can get is essentially a 1 minus P linear type of decay. And that's exactly what XRP's peer-to-peer overlay showed when the failures were actually random. So if the adversary randomly chooses the nodes that it will attack, essentially it cannot give any further damage to the network. If it fails 200 nodes, I'm looking at here, the remaining 750 nodes pretty much are still connected. So this is like a great picture from the perspective of robustness. With respect to random failures, we are good. But the situation dramatically changes when the adversary can actually choose more carefully the nodes that it is going to attack. And the optimal attack is a pretty difficult problem in general. So for a given topology, typically, it's an NP hard problem. We are looking at usually more heuristic type of strategies. One thing the adversary can do if it has the full topology knowledge is to attack the high degree nodes. And what happens in this picture is the robustness dramatically changes. Now, if the adversary fails just 100 nodes, basically the rest of the network has a largest connected component of size 200. Another way to look at it is the adversary is killing 10% of the nodes, but bringing with it another 70% that is now not the part of the largest connected core of this network. But there is another type of attack strategy that could potentially be even worse for the network, and that's attacking nodes that are high in their betweenness centrality. And betweenness centrality is a topology metric that looks at how frequently a node is participating in the shortest paths between among other nodes. So it basically looks at the situation where every pair of nodes in the network tries to communicate something with every other node, and a node with high betweenness will be basically participating in a lot of those shortest paths. You can view this more like a bridge type of nodes. And what you can see here is that the decline in the robustness of the network is not perhaps as sharp as the high degree attack, but in the high degree attack case, there was this diminishing return. Up until a certain point, there was a sharp drop, after which the high degree nodes being removed didn't really damage the network all that much. It looks like with the high betweenness attack, the adversary can actually, in a faster way, collapse the entire network. So this picture shows all three figures together. The random cases where the network is really robust. With respect to high degree and high betweenness, we see that it is quite vulnerable. And potentially this picture gives even an idea for an adversarial attack that could combine, you know, maybe a bunch of high degree and high between nodes could be attacked simultaneously to make this network even more vulnerable. So the bottom line for now is that random attacks, we are good with respect to maybe targeted attacks that aim for high degree or high betweenness nodes. There seems to be some vulnerability. The question is, can we do something? Can we propose maybe ideas towards improving the robustness of this system, maybe without significantly changing the topology, maybe adding just a few edges per node. So I did a lot of work on random graphs back in the days, and one idea that we brought from that prior research is this notion of random k-out graphs. I'll explain the construction. It is actually pretty easy. N nodes come together. Everybody chooses k other nodes uniformly at random and draws an edge towards that. And then in the end, we ignore the orientation of the edges and get an undirected graph. So if we are the network, I'm going to choose 2 out of you uniformly at random. You'll do the same independently. At the end of the day, the edges, the people we picked, will be forming, and the people who picked us will be forming our neighbors in this graph. What we found out in the past was that this is a really nice way to create a network that is sparse but connected. K equals 2 or greater is enough to ensure connectivity with high probability. And luckily, unlike most other random graph works, we don't have to go through the asymptotic regime where the number of nodes have to go to infinity. We can actually prove that this network is connected with 99.9% chance, even if you do it with just 16 nodes. If you do this construction with 20 nodes, you can add another 9. If you do it with 25, you can add another 9, and it goes like that. So one thing to perhaps keep in mind is that if you ever need a construction that is going to be decentralized and you need something connected with few edges, this type of construction could be a good idea to keep in mind. So, you know, this seems like not a bad idea, and if k equals 2, average degree is going to be just 4. What we tried was that if I add what is the existing XRP's peer-to-peer topology, a random k-out construction, can I dramatically improve its robustness? Random attacks was already fine. Can I dramatically improve the robustness to targeted attacks? And it turns out that actually we can. With respect to random attacks, we don't get to improve it even if we add those edges towards the using the random k-out construction, because it was already as robust as a network could be. But when it comes to high degree attacks, you see a significant improvement in the robustness when we add those 4 edges per node on average using the k-out construction. And with the high betweenness attack, still we can dramatically improve the robustness to those targeted attacks. I mean, we never get to the point as good as the random attack strategy, but still the improvement is, again, with those targeted attacks. If you go with the original, the network seems quite vulnerable even when the number of or percentage of nodes attacked is around 10%, but that vulnerability disappears by, again, adding the K-out construction. So the conclusion is mainly that the XRP's peer-to-peer overlay seems to be pretty robust with respect to random failures, but not so robust with respect to targeted attacks. And some simple idea using random K-out construction seems to improve the robustness significantly. And future work could be focusing on whether K-out construction could be enforced or encouraged, somehow incentivized from the get-go. And also basically can we go further and try to optimize. K-out is one idea, it seems to be a good idea, but could there be other options to improve the robustness even more efficiently? And actually we have an ongoing project on this last bullet. I didn't have the time to talk about that, but we are extending this research to not the peer-to-peer overlay, but the XRP's path-based settlement network, the transaction network as well, and maybe some more results on that would be presented perhaps next year. Yeah, thank you so much.